Hello, welcome back. Today we're going to be solving a few more problems having to do with singular value decomposition. And so here's our first problem. It is consider q of x equals all this. First, we want to find the maximum value of q of x subject to the constraint x transpose times x equals 1. B, find a unit vector u where the maximum is attained. And C, find the maximum of q of x subject to the constraints x transpose times x equals 1 and x transpose times u equals 0. So first, we want to be able to get this in a form where we can actually use it. So we want to turn it into a matrix. And we do that by, we take these first three, so x sub 1 squared, x sub 2 squared, and x sub 3 squared. We take those coefficients and we put those on our diagonal. And then the remaining ones are going to be what fills in around the diagonal. And we're going to divide them all by 2 because there's going to be one on each side. So it's a symmetric matrix, meaning that if you go along the diagonal and you fold it in half, it's going to match both sides. So to know where they go, we have 6, x sub 1, x sub 2. What I like to do is I like to count 1, and then 1, 2, 1, 1, 2, and that's how we know where it goes. So we put 3's there. And then for 2, it's x sub 1 and x sub 3. So we count 1, 1, 2, 3, 1, 1, 2, 3. So that's how we know they go here. And finally, for the 2, we have x sub 2, x sub 3. So I count 1, 2, 1, 2, 3. And we have our 1 here. 1, 2, 1, 2, 3. And we have our 1 here. So that's how we set up our matrix. And now we can start solving for A. So when it says find the maximum value of q of x subject to the constraint x transpose x equals 1, what it's really asking for is just to find the maximum eigenvalue. So we're just going to find the eigenvalues and then we find which one is the largest. So we have our matrix here that we just made. To find the eigenvalues, we take the determinant of A minus lambda times the identity matrix and take the determinant of that. So we have this. Subtracting each part, we get this matrix, and we can take the determinant of that. We know how to do that. So we come up with this characteristic polynomial, this characteristic equation, negative lambda cubed plus 11 lambda squared minus 28 lambda. We can take out a negative lambda so that we have lambda squared minus 11 lambda plus 28, and we can factor that. So we have negative lambda times lambda minus 4 times lambda minus 7 equals 0. So we get that our eigenvalues are 0, 4, and 7. And so looking at those, we see that 7 is the largest eigenvalue. So that is going to be our answer. And then part B, we're going to find a unit vector u where this maximum is obtained. So basically, we're going to find the orthonormal eigenvector corresponding to the largest eigenvalue. That's what we do. We had that A minus lambda times the identity matrix. We're just going to plug in what we found for lambda. So A minus 7 times the identity matrix. So along the diagonal, subtract 7 from our matrix. And then using row operations, we know how to do those. So I'm not going to show each step. So using our row operations, we come to this. And now we just solve for x1, x2, and x3. And so I like to write out what each of the equations are. Since we see that these are all zeros, we have x3 as free, and we can write x1 and x2. We can write x2 in terms of x3, and then we can also write x1 in terms of x2 and x3. So writing x2 in terms of x3, we have this, and then we get this. And I like to just choose an easy number to actually be able to solve for these. Set x3 equal to 1. And we can start solving for x2. So plugging it in, we get that x2 equals 1 as well. And now that we have x2 and x3, we can solve for x1. So plugging in our values, we get that x1 also equals 1. So we have our unit vector 1. But now we have to normalize it, meaning it has to have a length of 1. And so this is how we normalize it. This is finding the length of u, so we take u and divide it by the length of u. And so solving for u is just the square root of each of these squared. So 1 squared plus 1 squared plus 1 squared is the square root of 3. And so then 1 over 3 times u. So we just divide each of these by square root of 3, and this is what we come up with. And we can check that it is normal by finding the length of it. So 1 over square root of 3 squared plus 1 over square root of 3 squared plus 1 over square root of 3 squared, all under a square root, and we eventually get that it does equal 1, so it is normal. And so now for part C, we want to find the next maximum value under these two constraints. So we have x transpose times x equals 1, and x transpose times u equals 0. So length 1, and it is without 1. So this is basically just the second largest eigenvalue. And looking back at our previous eigenvalues, we had 0, 4, and 7. So the next largest one is 4. So that's how we can solve that. Going on to our second question. It's a little blurry, sorry about that. So we want to find the singular value decomposition of the matrix, and it is A equals -3, 6, 6, 1, -2, -2. And we are given a hint for one choice for u, and we'll solve for that later. So ultimately, what we want to find is A equals u times sigma times v transpose, and this is the single value decomposition. So our first step is we're going to calculate A transpose times A, because we have A here, but to be able to do anything with it, we want it to be a square matrix. So that's why we multiply it by the transpose. So remember, transpose is you take the rows, make them into columns. So this is A that we were given, this is A transpose, -3, 1. Take that row, make it the first column, take the second row, make it the second column, third row is the third column. And then when we multiply these, this is what we get. 8, 1, -27, -27, and 9. Now we can actually use it. So our second step is to find the eigenvalues. To do that, it's determinant A minus lambda times the identity matrix. So this is what we're working with. This is what we're going to be using. So along the diagonal, subtract lambda, and then find the determinant. So the determinant is 81 minus lambda times 9 minus lambda, so these two, and then subtracted by these two multiplied by each other. And set A equal to 0. When we multiply everything out, we get this, lambda squared minus 9 lambda minus 81 lambda plus 79 minus 279. And those 279s will cancel out. And putting these two together, we get lambda squared minus 90 lambda equals 0. Pulling out a lambda, we get lambda times lambda minus 90 equals 0. And so our eigenvalues are 0 and 90. And so step 3, now that we have the eigenvalues, we can set up sigma. And sigma is comprised of the single values. And so how we get the single values is it's just the square root of lambda. And so we only have 2 eigenvalues here, but we know that this has to be a 3 by 2. And so we know this because it has to be the same size as A. A was a 3 by 2, so sigma also has to be a 3 by 2. So because we only have 2 single values, we just fill in the rest, these bottom 2 with zeros. Because we got sigma 1 was square root of 90 and sigma 2 is square root of 0. It's just the square roots of our eigenvalues. And square root of 90 can simplify into 3 square root of 10. So here is the first part of the singular value decomposition that we've calculated. Remember, A equals U times sigma times V transpose. So we found sigma. Now, using our eigenvalues, we can find our eigenvectors. So we know how to do this. Our first eigenvalue is 90. We just plug that into our A minus lambda times the identity matrix. And so it's 81 minus 90, negative 27, 9 minus 90, and then augment it with 0 so we can solve for it. We get this, and then using some row operations, we can simplify it into 1, 3, 0, 0. And so we have the equation x1 plus 3x2 equals 0. That means x1 equals negative 3x2. I like to put in this. X2 is free, so we can just choose any number. I chose negative 1, so negative 1, and then x1 equals negative 3 times negative 1, so it equals 3. So this is our first eigenvector. Then our second one, with lambda equals 0, we have 81 minus 0, negative 27, 9 minus 0, augmented with 0. Simplifying, using our row operations, we get 3, negative 1, 0, 0. And so to be able to solve for those, we have 3x of 1 minus x2 equals 0. So that means x1 equals x2 over 3. And I like to, x2 is free, so we can set that as anything. I want to be able to get rid of that fraction, so I set x2 as 3, so that x1 would become 1 when we plug in 3 for x2. And now we have to normalize them. Again, normalizing just means that it has a length of 1. And so to normalize it, you divide each vector by its length. Or you can it's the same thing as multiplying it by 1 over the length. So we'd multiply each piece by 1 divided by the length. So starting with our first vector, we have 1 over the square root of 3 squared plus negative 1 squared times that vector. So this becomes 1 over square root of 10 times 3 over negative 1. So we get 3 divided by square root of 10, negative 1 divided by square root of 10. So that's our first orthonormal eigenvector. And then our second one, which was this vector, is 1, 3. We get 1 over square root of 1 squared plus 3 squared times 1, 3. So we get 1 over square root of 10 times the vector, and we get 1 over square root of 10, 3 over square root of 10. And you can easily check them. Just do a quick little dot product of them, see that they're orthogonal to each other, and that they're normal, that their length equals 1. So now that we have these two orthonormal vectors, eigenvectors, we can construct V transpose. So our third piece of the singular value decomposition. And we start by finding V. It's just V1 and V2. So what we just calculated up here, we're just gonna put into this matrix together. So it's 3 over square root of 10, negative 1 over square root of 10, 1 over square root of 10, 3 over square root of 10. And then we just find the transpose of that. So we take the first row, make that into the first column, second row is the second column. So now from the equation A equals U times sigma times V transpose, we found 2 out of 3 of the components. So now we're left with finding U. And so that's what we're going to do next. This is how I find U. We have our first vector, second vector, and we have our single values, which are these. So now we're just going to put everything together. And so we're just going to multiply each part. It's like we're going to find this part, and then we're going to find this part for however many parts there are. And so it's 1 over the singular value times A times our first vector, this one, and then 1 over our second singular value times A times our second vector, and so on. So this is just a quick reminder. This is what A is, this is what V is. Our first singular value, remember it's the square root of the eigenvalues. And so our first eigenvalue was 90. So the singular vector was square root of 90, simplifying down to 3 square root of 10. So when we're putting everything together, we have 1 over 3 square root of 10 times A times our first vector in V. And from this, we get negative 1/3, 2/3, 2/3. So that's going to be our first column vector of u. And then now we would go on to our second singular value, which we got s squared root of 0 because our first eigenvalue was, or our second eigenvalue was 0. But when we are plugging this in, we see that it is 1 over 0, and we can't divide numbers by 0. So we can't do this. So we have to find another way of coming up with the other eigen, those other column vectors of u. So this is what we have so far. We have sigma, which are the single values, and we have our v transpose, which is made up of our orthonormal eigenvectors, and we have the one column of u that we've calculated so far. So if we look at it to figure out how many columns we actually need of u, we can look at the what our matrices are. So we see that sigma is a 3 by 2 and the v transpose is a 2 by 2. And these can multiply together because we see these inner numbers match. So it's 2 and 2. So when we multiply these two together, we're going to get a 3 by 2. And to be able to multiply this 3 by 2 by this 3 by something, we don't know what, this is how we figured it out. So it needs to be 3 because it has to match this number. So we have to find two other column vectors for our u. We're going to do this by setting up some equations. So this is our first column that we calculated, just like earlier. So we're just going to multiply that by x1, x2, x3, set it equal to 0. So we have this equation, negative 1/3 x1 plus 2/3 x2 plus 2/3 x3 equals 0. And we're going to solve for x1, get x1 by itself. So in the end, we come up with this equation, x1 equals 2x2 plus 2x3, leaving x2 and x3 free. So this means we can set any values as x2 and x3, that makes sense, to find two orthonormal column vectors of u. So for our second vector, I'm going to set x2 equal to negative 1/3 and x3 equal to 2/3. So when we plug those in, negative 1/3 times 2 plus 2/3 times 2, we're going to get x1 equals 2/3. So this is our second column vector of u. And then for our third one, I'm just going to choose two more values. That makes sense. X2, I set to 2/3, and x3, I set equal to negative 1/3. So when we plug that in, we get x1 equals 2/3. So this is our third column vector of u. And so this is what we have in the end. We have A equals u times sigma times v transpose. And we can easily check this answer by multiplying them out. We see this is a 3 by 3 now, which can be multiplied by this 3 by 2, which will get us a 3 by 2, and the 3 by 2 can multiply by a 2 by 2, so everything can multiply. And so now it's just a matter of doing the math. We get this. This is what we get in the end. It's just scaled by 1/10 to get our original A. So it checks out. So we found in the end, we found the singular value decomposition of A. And we're going to do one more of those problems. So this is our last problem. It is another singular value decomposition of the given matrix. This time, they give us one column of u as a hint. And so we're just going to do the same process as we did before. We have A, but it's a 3 by 2. To be able to find eigenvalues or anything, we need it to be a square matrix. So we do A transpose times A. A equals this. A transpose, again, taking that first row, making it the first column. Second row is the second column. Third row is the third column. So A transpose times A gets us this matrix, this little 2 by 2 matrix, 2, 0, 0, 3. And so now the eigenvalues. When it is an upper right triangular, we know that the eigenvalues are on the diagonal, so we don't have to do the determinant of A minus lambda I. We can just take the values off of the diagonal because under each pivot is a 0. There's only one pivot in this case. that has a 0 under it. And so we have our eigenvalues 2 and 3. Getting the single values from that, remember the single value is just the square root of lambda. So our first single value is the square root of our first eigenvalue. So it's just square root of 2. And then our second single value is the square root of our second eigenvalue. So square root of 3. For single values, so using those, we're going to construct sigma. Once again, A was a 3 by 2, so sigma has to be a 3 by 2. So we have single value 1, single value 2. We're just going to fill in the rest with zeros to make it a 3 by 2. So this is what our sigma is. It's our first single value and our third single value. Now we're going to move on to the eigenvectors. So starting with lambda equals 2, we get 2 minus 2, 0, 0, 3 minus 2, which comes to 0, 0, 0, 1. So we have x1 is free because it's all zeros. And we have x2 equals 0 minus 0, x1. So just set x1 equal to 1. You can set it equal to whatever value you want it to be. 1 is just easy. When you plug it in to find x2, you just get that x2 equals 0. So that's our first eigenvector. It's 1, 0. And remember these eigenvectors, they're going to make up the v so that we can find v transpose. And so these vectors have to be orthonormal. So quickly checking that it's normal, we see we would do square root of the square root of 1 squared plus 0 squared, which is just square root of 1, which is 1. So it has length 1, so that's normal. And then going on to our second eigenvalue for finding our second eigenvector, we have lambda equals 3. So 2 minus 3, 0, 0, 3 minus 3. So we get negative 1, 0, 0, 0. This leaves x2 as free, and so x1 equals 0 minus 0x2 over negative 1. So again, you can choose any value you want for x2 because it's free. I just choose 1. It's simple, it's easy. Plugging it in for x1, you just get 0. So it's 0, 1. Checking this one is normal. We would get square root of 0 squared plus 1 squared, which is just square root of 1. It's also has a length of 1, so it's normal. And then are they orthogonal to each other? You dot product them, so that's b1 times 0 plus 0 times 1, it equals 0. So these are two orthonormal eigenvectors, and they can be used for our vector v. So v is made up of v1 and v2. We just found v1, v2. So it's 1, 0, 0, 1. Then finding v transpose, it's the transpose of that. That first row becomes our first column, second row becomes our second column. It just happens to be it's the same as original v. Now we can start to construct u. We've found of the singular value decomposition, A equals u sigma v transpose. We found sigma, we found v transpose, so now it's time to find u. So we see u is 1 over the singular value times a times vector 1, 1 over the second singular value times a times vector 2, so on. And we'll find out later how many column vectors we need in u. So just starting off, our first singular value was square root of 2. This is our a, and this is our first column vector of v. Multiplying those together, we get 1 over square root of 2, 0, negative 1 over square root of 2. And then going on to our second one, our second singular value was square root of 3. This is our a, this was our second column of v. So multiplying these, we know how to do that. It is 1 over square root of 3, 1 over square root of 3, and 1 over square root of 3. So this is what we have so far. This was our first column vector view, our second column vector view. But how many more vectors do we need? So to be able to be multiplied with sigma, which was a 3 by 2, this is a 3 by something multiplied by 3 by 2. We know that the inside numbers need to match, so it has to be a 3 by 3. So now we have to find that third column vector. And we were given that hint in the beginning. We were given that this could be used as a column vector of u. So we have 1 over square root of 6, negative 2 over square root of 6, 1 over square root of 6. So because we were given that, we just need to check to see if it's orthonormal with the other column vectors we calculated. And so first, does it have a length of 1? We do 1 over square root of 6 squared, which is 1 over 6, plus negative 2 over square root of 6 squared, which comes out to be 4 over 6, plus 1 over square root of 6, which is 1 over square root of 6. So when you add those together, yeah, and then you square root them all. It should equal 1. And then see if they are orthogonal to these other two column vectors that we calculated. To do that, you do you do the dot product. So just checking out against our first one, doing the dot product, we get this times this plus this times this plus this times this, and we should get 0. So 1 over square root of 2 times square root of 6 minus 1 over square root of 2 times square root of 6 equals 0. And then doing the same thing with the second column vector, we see that it is 1 over square root of 6 times square root of 3 plus 1 over square root of 6 times square root of 3 is 2 over square root of 6 times square root of 3 plus negative 2 over square root of 6 square root of 3. It equals 0. So having checked that, we know that is good for our third column vector. And then we found everything. So we found u, we found sigma, and we found v transpose. So now we can just do our final check just to make sure that the math was right and that it works out. So we can see it's 3 by 3. We can multiply these to get together. We should get a 3 by 2. A 3 by 2 times 2 by 2, that works as well. So we should be able to multiply them. So multiplying these two together, I got 1, 0, negative 1, 1, 1, 1 times v transpose. You get 1, 0, negative 1, 1, 1, 1, which matches with our A. So we know that it is correct. And we have found the singular value decomposition of our matrix A. That is everything. Thank you for watching, and I hope you have a good night.